So, we continue with our discussion on clocking and clock distribution again. So, we start now by introducing some terminologies, then we shall be moving on to some actual clock distribution, or you can say layout algorithms or strategies, how it is done. So, we introduce some terminologies which we shall be using in some discussions later. So, we define a clock network, a clock net or a clock routing instance as represented by a net with n plus 1 terminals, where there is one source called S0 and there are n terminals S called sinks. So, diagrammatically it will look like this. So, I have a source S0 and there are n sinks S1, S2 to Sn. So, I have to lay out a net like this. The S1 has to be connected to all S1, S2 to Sn. This is a net which is I am indicating by S. This is a set. Okay. So, given a clock net, so we are looking for a clock routing solution, because ultimately from the clock source S0 we have to use a set of wire segments to connect the terminals. Like, see, this is the problem, that S0 has to be connected to S1, S2 to Sn. Now, there are so many ways, like for example, I can say that S0 I can connect by straight lines to all of them, or I can connect by vertical and horizontal line segments, something like this, and so on. So, there are so many ways, right? So, this is the final solution I want to arrive at, and this I refer to as a clock routing solution. Okay. So, the clock routing solution is actually the set of wire segments that will allow us to make this connection. Now, in this clock routing solution, there are two different sub problems you can think of. One is referred to as the topology, other is referred to as the geometric embedding. Like, I shall be illustrating them with an example, but let me explain it first intuitively. Topology means the kind of clock tree I talked about. So, how the clock tree will look like, that will be my topology. Like, every driver is driving 2 other drivers or 4 other drivers, that will be the topology that I am talking about. And once I have the topology, I have to actually connect my physical clock terminals, the sinks, to some leaf node of this tree. That is the geometrical embedding. So, exactly geometrically where do I place this? The tree is general in nature and geometrical embedding is more specific, depending on the exact location of the clock terminals, right? Okay. So, when I say a clock tree topology, it is a rooted binary tree with n leaves corresponding to the set of links, and internal nodes, as I said, that I have to connect them by horizontal and vertical line segments. So, it will be like a Steiner tree. So, all the internal nodes of the tree will be referred to as Steiner points, they will have to be connected. Just diagrammatically let me illustrate. Let us say I have a clock routing problem instance. Let us say this is a small chip. So, I am showing these are the terminals which have to be connected, S1, S2, S3, S4, S5, S6, and suppose my clock source is somewhere in the center, S0 here. This is S0 and the remaining ones are the clock sinks. This is my clock routing problem instance. Now, first thing is that we just arrive at a topology. We are saying that let us have a topology like this, like S0 will be connecting to two intermediate nodes. Now, each of these intermediate nodes can refer to drivers. This U1 and U2 can be drivers. So, this U1 can drive this S1, S2 directly. This U2 can drive two more drivers, U3, U4, and each of them is driving two of them. So, in this connection topology, so one thing we are assuming that every node is driving up to maximum two other nodes. So, whenever you are designing the buffers, the buffer design will be like that. So, it will be driving a maximum of two other signal lines. So, the fan out will be 2. Okay. So, the buffers will be relatively smaller in size. Okay. Now, on this connection topology, so this connection topology we will be doing embedding on our actual problem. So, this is one possible solution of embedding. Like what we are saying is that these are the points which are already there, and this is the connection topology that we want, and this is one possible interconnection that we do to achieve this. Let us say this one from S0 to U1, then S1, S2. So, I am showing it like this. This node may be U1 and this S0, and this connects to S1 and S2. Then U2 goes to U3 and U4. Let us say this one is U2, this goes to U3 here and U4 here. U3 goes to S3 and S4, S5 and S6. So, this embedding, you see here you get not only the exact connections, but also the location where the buffers have to be placed, U1, U2, U3, U4. Okay. This is a solution which shows the location of the buffers as well as the geometry of the interconnection lines, right. Okay. So, clock skew you already know of. So, it is the maximum difference in clock signal arrival times. Like you see, I say that I have a clock source S0. So, I have so many sinks S1, S2, in general SI, there are n sinks. So, the delay between the source and the sink I refer to as T S0 Si. So, if I calculate this delay across all S0 and Si pairs, S0 S1, S0 S2, S0 S3 and so on, and take the maximum of them, that will give me the maximum skew, right. So, mathematically we are expressing it like this. The total skew will be maximum of the differences. So, what is the maximum difference in the delays between any pair of I and j? So, the delay between S0 and Si, S0 and Sj, their difference maximum across all Si Sj pairs, that will be defined as my maximum clock skew. Now, we define two terminologies, local skew and global skew. See one thing, we are talking about the clock signal which is going to all parts of the chip. Let us say, so I have a chip, let us suppose these are some of the clock terminals here, there are some clock terminals here, there are some clock terminals here, there are some clock terminals here, right. See, these clock terminals refer to some flip flops or some storage elements. Now, let us assume that these 5 dots I have shown here, they correspond to some storage cells which are connected among themselves. These 4 refer to some storage cells again which are connected among themselves. They refer to storage cells which are connected among themselves. So, what I mean to say is that for correct operation, so we must ensure that in every zone the flip flops which depend on each other, there should not be too much skew among themselves. Similarly, in this zone or this zone, this skew has to be limited. But if you take a point here and a point here, they correspond to two storage elements, but they are not directly connected. So, even if there is a considerable skew between these 2 points, that will not affect your circuit operation. So, what you mean to say is that although theoretically skew seems to be not a good thing, a bad thing in fact, but all skews may not be equally important. Skews that correspond to some local area of the circuit, which corresponds to, suppose, a pipeline, storage stages with combination circuits in between, they skew between those stages should be important for you. But one pipeline and another pipeline somewhere else, they may have some significant skew among them also, that will not be a problem, right. So, local skew we define like this. This is the maximum difference in the clock arrival time. Locally means at the clock pins of a set of related sinks. Related sinks means the storage cells which are somehow connected among themselves. So, typically local skew corresponds to the sinks which are within some distance, limited distance. They often refer to, as I said, storage elements that are connected by a directed signal path. What is a directed signal path? The output of a flip flop is going to the input of a flip flop via some combinational circuit, that is referred to as a directed signal path, right. So, this is local skew. So, if you now look at global skew, global means I am looking at it across the chip. Maximum difference in arrival times correspond to any two sinks, they may be related, they may be unrelated. So, here with respect to the whole clock distribution network, we are looking at the difference between the shortest and the longest source sink paths. So, when you refer to as skew, we actually refer to as global skew, but for a practical problem, local skew can be more important to you, because you need not minimize skew globally. For better performance, you can concentrate on the local elements and try and limit skew on those, on those local elements only, right. Fine. So, some terminologies for clock skew, clock tree routing. Well, first sub problem, this is of course desirable and the ideal situation, zero skew. So, we try to create a zero skew tree. Like when I say that from a source I create some kind of a tree, so I am not showing the buffers here, the buffers will also be there. So, let us take a very small example with 4 sinks. When I say it is a zero skew tree ZST, it means that the delays from this S0 to each of S1, S2, S3, S4 are all equal. Of course, as you can understand, this is an idealized situation. You can try to make the delays equal, but in practice, because of variations in parameter and variations in parasitics, there will be small differences in delay, right. But you make your best effort to make the wires equal, or you can consider the parasitics, the R and C. So, your wire length equalization may not be the main parameter, but RC delay equalization, that can be more accurate in that sense, you try to equalize them. So, if you are able to do that, you will get something which is referred to as zero skew tree. But as I said, computing zero skew tree is not easy, it is difficult, and some variation in the parameter during fabrication can deviate this zero skew characteristics in an actual tree design, right. So, in practice what you typically may want to have not exactly 0 skew, but bounded skew. Let us have a clock tree where skew is limited to certain maximum limit. Well, we shall later see that during the back-end design we have a process called sign off, means we analyze all timing delays, the relevant timing delays in the circuit, and we say that everything is in order if the maximum delays are within certain limit. So, this bounded skew model helps us not only for the final sign off, but also during intermediate steps that can help in reducing the length of the tree, because you see, to make a clock tree exactly 0 skew, maybe you may have to make some tree lengths longer. Like it may so happen that let us take a hypothetical example, that from one point you are drawing a line to a point S1 and another line to a point S2. So, although it looks like the lengths are equal, but there can be some parasitic resistance and capacitance effects, right, and these parasitics may not be the same for both the lines, because it depends on the lines which are running parallel to those lines on the same layer across different layers. So many other factors are there. So although the wire lengths are the same, the capacitive and resistive effects may be different. So, it may so happen that the delay of the second line, let us say the delay of this line is delta 1 and this line is delta 2, it may so happen that delta 1 is greater than delta 2. So, for that purpose, to equalize, sometimes we may have to do something called snaking. This is a term which is used, which means instead of laying this wire like this, maybe you will be laying it like this, make this wire length longer, so as to match the two delays, try to make delta 1 and delta 2 approximately equal, right. Fine. So, here the problem with bounded skew is sometimes referred to as BST or bounded skew tree problem. And useful skew means, as I said, that although we talked about skew across arbitrary points, which is the global skew, but in practice local skew is more important. So, if you can handle the local skew and try to reduce them, that will perhaps provide us with a solution where we can run our circuit with a very high clock frequency. Global skew may not be that important in that respect. Okay. Now, coming to the modern clock tree synthesis, let us look at what are the basic steps which are carried out and some suggested algorithms, some important algorithms which are used in the process. Let us look at. So, for modern clock tree synthesis, there are two main requirements. The first requirement is of course relatively easier, and we shall be looking at this in some detail, that how we can construct a tree where the skew is either 0 or limited, bounded, okay, and how we can introduce the buffers in the presence of variations. So, the clock tree should have low skew, so while delivering the signal to every sequential block, this is the main requirement. So, we shall be looking at various ways of designing the clock tree such that the skew is either 0 or very close to 0, bounded. So, when we talk about clock tree synthesis, so it is performed in two steps. So, we construct the initial tree. So, either we construct the tree not considering the sink locations. It is a very general tree which is applicable to designs which are independent of sink locations. Second alternative may be we consider the sink locations. Topology and embedding both we are considering together. Third, we consider them as two separate steps. We assume that a clock tree has already been built. Now we are talking about embedding, just like that grid structure I told you about, that I make a clock tree first, then I have a mesh or a grid, the clock tree is driving that mesh, and embedding means I have to tap that grid from appropriate points to take my clock signals, right? Okay. So after you do this, so you can insert the clock buffers whenever required, and you can carry out several skew optimization like that snaking example I told you about. You may have to make a wire slightly longer to match with the others. Okay. So now let us look at some of the clock routing algorithms which are used in practice. So the main objective behind this clock routing algorithms is to minimize the skew, which means how to distribute my clock signal such that from the clock source down to the sink, how I can ensure that my interconnection lengths are all equal in length. Well, the first approach will consider only interconnection length, but later on we shall see that not only interconnection length, we can also calculate the parasitics, we can measure the actual distance or estimate the distance, and you can try to actually the delay, we can estimate the delay based on the distance and the parasitics, and you can try to balance the delays, right. So to start with, the first few algorithms we talk about, they will be looking at only the distances, they will try to equalize or match the distances, right. So we shall be talking about several algorithms. The first 4 of them, for instance, they try to minimize the length. The last one, of course, they look at actual zero clock skew by carrying out more accurate estimates of the delays. So let us see these one by one, right. Okay. The first algorithm we look at, this is referred to as H tree based algorithm. See, H tree based algorithm, the name comes from the letter H in the English alphabet. So clock routing takes place in a way that looks like the letter H, like suppose I have an H like this. This is what I am referring to. This is like a tree. For example, I feed my clock and I get my clock in these 4 places. So this H, logically speaking, is like a tree with 4 child nodes. Now what you can have after that, from each of these terminal points, you can have a smaller h like this. So you get another 4 points from each of them, right. So from each of them you get 4 child nodes and so on. So your clock tree will look like this. This is called a, this is not a binary tree, this is a 4-array tree, which means every vertex has up to 4 children. And one constraint is that as you go up in the various levels, suppose this is your level 1, this is level 2, then level 3 you go. So in level I will have, you can check 4 to the power I nodes. First level there are 4 nodes, 4 to the power 1. Second level there are 16 nodes, 4 to the power 2. Third level there will be 64 nodes, 4 to the power 3, and so on. So this kind of a clock network you can build only for those cases where there will be 4 to the power I nodes. But there are some advantages we shall see. Let us come back to the slides. So in this approach we shall see that the distance, the geometric distance from the clock source to each of the terminal points of sinks is guaranteed to be the same. Well, loosely speaking, this kind of approach can be used for scenarios where you need a large number of clock terminals and they are all arranged regularly all across the chip, like for example in a gate array or an FPGA. But also you can use this for the 2-level routing. As I said, you have a clock tree which feeds a grid or a mesh. You can have this H tree as the first level tree. So it regularly feeds the clock to regular places which will be connected to the grid. That is also one way. So this can also be used to carry the signal to various regions or zones. So let us look at these H shapes in terms of the geometry. So here the grid lines are shown. Let us say this H, the center points, the terminal points are placed like this. Then from this point up to each of the terminal points you can check the distance will be 1, 2, 3, 4, 5, 6, 7, and if you look at the center point it will be 4, 1, 2, 3, 4. So either from the center point or from this entry point the distance up to each of these nodes will be 7. So if you construct this H up to another level and if you calculate the distance similarly, the distance will be 19, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 15, 16, 17, 18, 19 like this. So from this point down to each of the terminals the total length of the wire is guaranteed to be equal, and as I said this can be generalized to any power of 4. This is 4 terminals, 16 terminals, so you can go up to 64 terminals, 256 terminals like this. So as you can see, as you go up and up you get a structure where the terminals are very regularly spread all across the chip. So in any scenario where you need the clock terminals to be distributed regularly across the chip, you can use this method or this principle. Now another thing you can also check that this connection or the routing is such that all the wires are connected on the same metal layer. You do not need to move from horizontal to vertical, vertical to horizontal on 2 layers. It is a purely planar routing. The entire connection you are carrying out on a single plane and you are guaranteeing equal distance from the source to each of the sinks. This is a big advantage for H tree. So what do you guarantee here? Exact zero skew. Well, in terms of the distance, here we are ignoring the parasitics RC for the time being. Exact zero skew with respect to the length of the wires because of the symmetry of the tree. But as I said, this H tree is typically not used for the entire clock distribution. This is used for the top level clock distribution. The top level, this H tree can feed that grid structure, and that grid can in the second level used to feed the other points or other pins of the circuit. Now if there are blockages on the layer, then the design of the H tree will be spoiled. That is why I said, so whenever you are laying out a clock tree, that has to be laid out on a separate metal layer where there are no blockages. You can lay out the lines as you want. Okay. And also if the sink locations and sink capacitances are vary, then the design of the H tree will be different, because here you are saying exact zero skew only with respect to the distances. Okay. Well, now another thing you just observe, suppose you consider an H. So this was an H tree which is connecting these 4 points, and suppose this is the central point from where the clock is coming, let us say. Now what I am saying is that because we are laying out all the connections on the same layer, so I do not have any compulsion that the wires have to be horizontal and vertical only. So I can also run the wires diagonally if I want. So here you see, just inside this H, my main requirements was to connect the points 1, 2, 3 and 4. So by doing this, I am making the wires longer. Why don't I connect them by straight lines like this? They will obviously be shorter, because this was this. If this is A and this is B, this will be square root of A square plus B square, Pythagoras theorem. This will be shorter. So if I want shorter connection, I can make it as an X instead of a H. So our next alternate algorithm, this is called X tree. Same thing, instead of that H type structure, we are using an X type structure like this. So I use a big X, and with each of the terminal points I use smaller x's. From each of them I will be using even smaller x's, like that, right? So we are assuming that we are allowed to lay out the wires which are non-horizontal and non-vertical also. Okay. So at first look you may say that, well, this looks better because the wire lengths are shorter, but there is a problem that is also there. Like you see, in an H tree the wires were so regular, they were symmetrical, but now here you see between these line and this small line, the wires are running closer together parallel. So there will be more capacitance between them, but between this wire and this wire there will be much less capacitance, they are farther away. So because of this slanted kind of connection, the capacitance between the wires which are running closer to each other will be varying from one segment of the X to other. So it will not be exactly zero skew in that sense if you consider the parasitics with respect to R and C. Okay. So this is one drawback, apparently better it may be, but there can be crosstalks due to close proximity of the wires. So again, H trees, just like H trees, you can use it for special structure, like creating the top level tree then feeding it to the next level, like that you can use this also. So this H and X trees are two alternative ways in which typically people build the first level clock tree before they are distributed to the different parts of the chip. So with this we come to the end of this lecture number 29. So we continue with other implementations of clock tree routing in our next lecture. Thank you.